wave function has. And we want to talk just a little bit about the coordinates in the Hamiltonian. So a particle could go in the x direction, the y direction, and the z direction, or any combination thereof, and it'll have kinetic energies in all three directions. So we have to have three one-dimensional kinetic energy operators. So we're going to have T of x, y, z plus V of x, y, z. And your curiosity should be building over why I have the Chinese coolie hats there. Okay. I probably exceeded all bounds of political correctness there. Okay. Phoebe will have to watch this in her dorm room and not let anyone see it. Those crass Americans, you know. Okay. Now, we can break the kinetic energy clearly into three pieces. So it's minus h bar squared over 2m, second derivative with respect to x, minus h bar squared over 2m, twice the mass of the system, d squared dy squared, minus h bar squared over twice the mass, d squared dz squared. There it is. Okay? Now, this is really the x kinetic energy operator in one dimension. This is really the y kinetic energy in one dimension. And this is the z kinetic energy in one dimension. And that fits with our intuition. We can have the energy of motion in the x, y, and z directions. So separate kinetic energy operators. Remember, we associated the energy of a matter wave with its curvature. If it has low curvature, it has low energy. If it has high curvature, it has high energy. These operators are going to interrogate this wave function to see how much curvature it has, and hence how much kinetic energy. Now,
what was it? Oh, that's a z, okay. You're like grabbing something down, breaking it up, grabbing that apart, breaking that up. I don't know if you know what I mean. It's just, there's a lot going on in just the very top Schrodinger equation.
Yeah, there's a lot going on, isn't there? And guess what? It's not going to quit. The fire hose is going to be turned on full force for the whole semester. It's going to be serious entertainment for serious students.
That's still subtraction, right?
So it all comes through with a minus sign. Okay. That's really important. H bar is h over 2 pi again. That angular form of Planck's constant. Now let's just write that down.
Well, at least it's all the same.
H over 2 pi. M is the mass of the particle.
Mm-hmm.
And the second derivative gives us x, y, and z curvatures. So this is a three-dimensional matter wave, and we're trying to get its curvatures. Now, here's something that's really kind of interesting. The kinetic energy operator always stays the same from problem to problem, from atom to molecule, from hydrogen atom to DNA. The kinetic energy operators stay the same. Now, you might need more of them. If you have 1 million electrons, you'll need 3 million of these one-dimensional operators, but they're all the same. All the uniqueness of a quantum mechanical problem occurs in the potential energy part. So these are the unique to each quantum problem. is the potential function.
What do you mean by that?
Different molecules have different potential functions. Different style. In other words, this can vary a whole bunch. The kinetic energy never varies.
Okay.
Okay, it's
From like-
always of this form.
From like particle to particle, that doesn't vary the kinetic energy?
Yes, any quantum system you want will have the same kinetic energy operator. Let's say you're looking at helium. You'd have you'd have 6 operators, 3 for the x, y, and z coordinates of electron 1, and 3 for the x, y, z coordinates of electron 2. And in that approximation, we'd assume that the nucleus is so heavy it's not moving. But if you wanted to put the nucleus in, it'd be 3 derivatives, x, y, and z for the nucleus. Okay? But this is unique to the quantum problem. What's the potential energy? You're learning it in physics right now. It's Coulomb's law between electron 1 and nucleus 2, right? In your DNA molecule, there's a nitrogen base pair, there's a nitrogen here, there's an electron there, and they're interacting via Coulomb's law. So electrons could repel one another, or electrons, let's say if we're dealing with molecular systems, could be attracted to or attract a proton. Okay, unique to the problem, all the geometry and so forth. Atoms are wonderful, by the way, because all atoms have spherical symmetry. All atoms belong to the same group. It's the KH group in your world of molecular spectroscopy. But getting the potential right is a real challenge, and solving the equation. I promised I'd tell you what the Chinese coolie hats were. It's common notation for the little hat. Means a quantum mechanical operator. In operator mathematics, the operator acts on the function to the right. Operator function. Eigenvalue, in this case, equals energy times the function. So, operator acting on the function spits back the energy times the function again. Okay? If we use other operators besides the Hamiltonian, we'll get other things besides the energy. We can get momentum, we can get position, we can get all sorts of stuff, depending on what we're interested in. But the really big one is this form. Now there's an alternative form, and let me specialize this just to, why don't you add the subscript in all of these. So this is the nth wave function, the nth eigenvalue or energy times the nth function back again. And one of the reasons why I like chemistry and physics students to take linear algebra is to learn about this operator function relationship. Now, you guys, as I recall, have had some calculus, but probably not linear algebra. Is that okay? Linear algebra, just without going into any detail, I'll teach you the linear algebra you need to know. But without going into any detail, this operator acting on a function to give a numerical constant times the function, that's really common in linear algebra. Okay. Now there's another way to write this. This is an extremely powerful notation developed by the Nobel Prize-winning physicist Paul Dirac. The guy was a genius in a social, he really struggled socially, as we mentioned. Hardcore non-believer, interesting character. Okay. Paul Dirac. And he figures prominently in the development of quantum mechanics. So this is his notation, and this, instead of writing the wave function psi n, we write it formally, we just put n right here. This is the so-called Dirac notation.
Oh damn, I thought that was an ln. Alright.
Now, this one, this is the Schrödinger form. Okay, so Dirac's a hardcore non-believer and a social outcast. Schrödinger knows how to entertain his mistress, invent wave mechanics, and deceive his wife over Christmas. There's some interesting people doing this, aren't they? Okay. And then there's Heisenberg. Now, Heisenberg said, hey, things look like this.
Are these just other guys writing it differently?
Yep.
Or are they like, is there a different way of solving and using this?
Okay, so this is the Hamiltonian.
Like, would you use Heisenberg's over Dirac's for a certain
Hold on to
equation?
that.
Or are these just guys like, I want to be part of this new era, let me just make something else up? Because I could have made something else up too that looked like...
Okay. So, let's look at these three giant figures in the development of quantum mechanics. Schrödinger, Dirac, and Heisenberg. Okay. So, Schrödinger formulated quantum mechanics in terms of a differential wave equation. You can take courses in differential equations. here at Concordia or at other universities to learn how to work with. So Schrödinger said, hey, this I can write differential equations that describe all this stuff. Dirac said, I can develop this formalism. This is formal operator theory. We have operators operating on eigenvalue. This is an eigenvector here for good old Dirac, this Dirac kit. Formal operator theory, we can do it that way. And then Heisenberg says, cast it into matrix form, the operator theory. So
Pass into matrix form?
yeah, matrix vector form actually. Let's add a vector down there. Now, on the surface, these look like three different ways that aren't related. But it turns out that all three methods are completely equivalent. They give the exact same predictions and final results, one to another, these three big types. Schrödinger, Dirac, and Heisenberg. Okay, now, we've told secrets about Dirac. So who is Dirac?
I thought he was the atheist.
He was a hardcore atheist and kind of a social misfit.
Mm-hmm.
Okay, what did Schrödinger do besides invent quantum mechanics and win a Nobel Prize?
He fooled
Scandalous.
around.
Scandalous,
Yeah.
scandalous mistress, fooled around, deceived his
Oscillations.
wife, entertained his mistress, and developed wave mechanics over a Christmas break. I just settle for inventing wave mechanics and get out the other two. Unless she's really hot and rich. No, don't tell this kid. Okay, now, Heisenberg, do you think there's some interesting social history with Heisenberg?
Something about making meth or something.
Oh, okay, no. Heisenberg was German.
Oh, he's a Nazi.
And Einstein drive fear Adolf Hitler wants the bomb. Wants the atomic bomb. And who gets appointed the head of Hitler's atomic bomb project?
We'll go with Heisenberg.
Heisenberg, yes indeed. Heisenberg is tapped by Hitler. Build me the bomb. I want to blow up the world and rule and rock and dominate. Now, by the way, all the scientists knew that Heisenberg was trying to make the bomb, and their conclusion was, we got to get it first. And so the whole Manhattan Project started up, and the United States got the bomb first. Germany got wiped out. Heisenberg was primarily a theoretician, and that compared to Great Britain and the United States, they weren't even close. They never really got that far. And there's to this day some serious speculation that Heisenberg deliberately drug his feet. He didn't want Germany under Hitler to get the bomb.
He just probably saw
Yeah, and it's easy enough in science to make it drag it out. So they didn't get very far. After the Second World War, all the German atomic scientists working on the project, they kind of threw them together under house arrest in this big house, and they bugged all the rooms because they wanted to hear the Germans talk.
Have we captured them?
Yeah, they captured all the scientists, took them back to Britain. And I mean, they were nice to him, they fed him and everything, they weren't torturing him, but you're going to stay here. And they wanted to hear them talk about the bomb effort. And they were absolutely astounded that the United States and Britain were able to pool their resources and make the bomb and make the Hiroshima and Nagasaki weapons are very different in construction and design. So they were absolutely amazed that the U.S. pulled it off. And you know, one of the thoughts was, my goodness, to make the bomb, we're going to have to turn the whole country into a big factory to do it. But that's exactly what the United States did. They had Oak Ridge, they had Hanford, the nuclear reactors at Hanford, they had Oak Ridge, Tennessee, and they had all this top secret stuff going on at Los Alamos, where I had a Q clearance and a security badge for 13 years.
Before the nuclear bomb, did we have the ability to harness nuclear power for like nuclear power plants using the energy?
Well, in 1942, Enrico Fermi, working at the University of Chicago, they did the first sustained nuclear reaction. They had that going as early as 1942.
Okay.
Okay. And so they figured out, oh man, and we can moderate this, we can let the nuclear reaction go and heat stuff up, we can heat up water and turn a steam turbine and generate electricity. Yeah, they had that figured out in 1942. And then the whole thing at Los Alamos, they were figuring out, well, how do we get enough of the right isotopes, get a critical mass, get it all together to make these nuclear weapons, which obviously they did.
Yeah.
And those were dropped in Hiroshima and Nagasaki. A very wonderful thing for the U.S. and for the world would be for a nuclear weapon never to be used ever again.
Yeah.
If you look at some of the, I'm off topic a little bit, but if you look at some of the pictures of Hiroshima and Nagasaki after the blast, and some of that, and then the Nevada test site pictures where they put cars and houses just to see what happens to them near a nuclear weapon, you just absolutely will conclude that. I mean, even ISIS doesn't deserve a nuclear weapon.
I'm sure they want one.
Well, I mean, it's the dream of third world terrorists to make a nuclear bomb, or at least a dirty bomb, for obvious reasons.
Yeah.
And the trouble is with CNC machine tools, it's pretty stuff that was really hard to make, you can make now.
I know.
It's a scary world we live in. Pray hard, we need it.
Yeah.
But anyway, that was Heisenberg. I got off the track. Perhaps deliberately drug his feet on making a German bomb. A good thing, for whatever reason, that didn't happen. Now, here in the 21st century, we might, in fact we will, use some aspects of all three systems of representing quantum mechanics. But primarily in this course, we'll stick with Schrodinger's formulation with appropriate references to these other formulations along the line. But we may put them together in certain times. Our book doesn't use Dirac notation all that much. I really like Dirac notation. I'll use it more than the book, but it'll be very clear. Every one of these things has some advantages, and like any tool in science, whether theoretical or experimental, the tool doesn't apply to all situations. You don't pound a nail into the wall with a screwdriver. A screwdriver is a perfectly good tool, a nail is a perfectly good fastener, but you know, if you have a nail to hammer in, you don't want to hammer it in with a screwdriver. And similarly, you don't want to pound a screw in the wall with a hammer. So we'll be guided in the selection of which of these forms of quantum mechanics by what the job is and which tool best handles that particular job. Now, in preparing for today's lecture, I quickly looked over what our book had, and then a more advanced book had, in terms of why quantum mechanics was just absolutely thrust upon us. And our book has truly an incredible summary of all these failings of classical mechanics that came up. It's unbelievable just how much was going wrong and how badly it was going wrong. Now, before we get too far down the line, we want to talk about old quantum mechanics. This is the quantum mechanics that arose from Niels Bohr in the early part of the 20th century. Didn't have the underlying mathematical structure that this had. And the idea that in atomic hydrogen, the electron has stable orbits, or what are called stationary states. These come from spectroscopy. S, P, D, and F are spectroscopic terms, and they underlie the orbitals that we know and love well, that we learned in high school and in college undergraduate chemistry were reinforced in. So this old quantum mechanics doesn't have H cycles, E psi, or a matrix form or an operator form in the spirit of Heisenberg or Dirac. But Bohr just said, hey, if you're in the 1s, you are stationary. Your energy is neither increasing nor decreasing. Now, this may not mean a lot to you, but I want to summarize an entire semester course in physics, electrodynamics. And I can summarize it verbally. Electrodynamics in the physics department is associated with the physics of moving charges, like electrons moving around a nucleus. It's a beautiful and complicated, mathematically rich subject. But I'll spare you all the mathematics. Basically, if a charge is being accelerated, and by the way, if you run something around in a circle, like Earth around the sun, or an electron around a nucleus, is there acceleration if particles going at constant velocity around the nucleus? Oh yes, there is. It's v squared over r. Now, one whole semester worth of electrodynamics, here's the one sentence summary. If charge is being accelerated, electromagnetic radiation is created. But if you're creating if you're cycling this thing, spinning it around and creating electromagnetic radiation, that's energy, and you're bleeding the energy off of the hydrogen. The fact of the matter is, the hydrogens will stay there forever. There's no energy, but the electrons orbiting. And Bohr said, hey, if in certain cases the electron acts like it's stationary, it's not liberating any light. These are stable, stationary orbits. The electron seems locked, if you will, and there's no radiation, and we call those stationary states, and you know them by the name S, P, D, and F.
Just orbitals.
Orbitals. stationary because we're not radiating any energy out. They're stationary. And so Bohr just kind of put this all together without any.
But there is an electron in that orbital.
Oh yeah, there's an electron there, but somehow it's stationary. Now, you could do it this way. You could say, hey, the electron's really a wave, and it's a standing wave.
Yeah. So as soon as you look at it,
and then the imagination struggles to, well, what does a stationary electron look like? So Bohr, through some brilliant deductions and guesses, said, hey, I don't care if classical electrodynamics, if Faraday and Maxwell is as hot of professors as those guys were. Phoebe, those were guys from London and about. So they were from the old country, really good. So they said, hey, accelerated charge radiates. Energy is being dissipated. Bohr said, no, it's not. Not when in a stationary orbit. And he just kind of artificially said, no, it's not. And then he got S, P, D, and F orbits. And the kinds of things that you were looking at this morning in molecular spectroscopy laboratory, we're going from one stable orbit to another. And in that case, energy is allowed, and you see the color.
mm-hmm.
Okay, so this is known as the old quantum mechanics due to Bohr. Brilliant, intuitive deductions. Then we have Schrödinger, Dirac, and Heisenberg. All about the same time, I might add. This was all getting worked out in the 1920s. This was the Roaring 20s and the Great Depression, and about then it was all getting worked out. So it's about 100 years old. Okay, little over 100 years old. We mentioned last time that quantum mechanics and relativity aren't fitting together all that well, and they're still not fitting together all that well after all these years. Okay, so, but we're not going to concern ourselves with relativity, at least to start with, and we may graft on the relativistic effect of spin a little bit later on in the procedure, and then we'll take a peek at what electron spin is and how relativity does come in some more. Okay, hold on, we've got, what, 15 more minutes of fun. Okay, all right. Now, I think we're ready to do some real, in the last 15 minutes of the hour, some real applied quantum mechanics. The real deal. And you'll be happy to know I'm going to choose one particle quantum mechanics in one dimension to start with. Aren't you relieved? And then we'll let all hell break loose, and we'll be down there with Dirac. We'll let all hell break loose. And we'll go to multi-particle systems.
And we're going to be using Schrödinger's equation?
Well, we're going to use the Schrödinger form, yes. By the way, the Heisenberg form, the matrix form, is really powerful if you're going to program computers to do quantum mechanical calculation. So, very, very powerful.
And this was far before computers as well.
Yeah, the development of quantum mechanics predated computers, but very early on, people recognized that some of these problems couldn't be solved, and you would need computational ability to do it. And there were two guys. One was named Hartree, and the other guy was named Fock. And Hartree and Fock, I know it sounds bad, but that's the guy's name. they developed a way to approximate solutions, you can't get them analytically, of multi-electron systems in large atoms and in molecules.
Yeah.
And it's called the Hartree-Fock method. And it's an iterative method where it cycles through, and man, when computers came around, people really jumped on the Hartree-Fock method and refinements. And in part of my doctoral dissertation, I was doing refinements, taking things well beyond the Hartree-Fock method. Now, one thing I did in my career is I actually didn't like computational quantum mechanics. And so I said after I got my PhD I was going to switch fields, which is common. And I went into hardcore chemical physics, lasers, experimental chemistry. And as my postdoctoral advisor so beautifully said, he says, I'm going to let the molecules solve Schrödinger's equation for me through experiment. And I think that's just a priceless quote. You know, like, I don't have to go through all the details, I'll measure the darn spectra, and then we'll know what the eigenvalues and the eigenvectors are, and what the wave functions are. And that's what I chose to do. But my strong background in quantum mechanics has always been a very good thing. Okay, now, real quantum systems. So let's look at a free particle in one dimension. It can go from minus infinity to plus infinity, and it's plus light year, so aptly quoted, and beyond. Okay. So imagine this electron on a very long, thin wire. I mean, this wire would stretch across the galaxy, let's say. So straight as an arrow for millions of miles each direction. Okay? And we're going to assume everything in the wire is the same and there's no potential energy. So V of x equals 0. No potential energy. Well, what's T of x? We have one particle of mass m. What's the kinetic energy operator?
Kinetic?
Mm-hmm.
H.
Okay,
Half.
minus h bar
H
squared
bar, sorry,
divided by
pi.
2m.
Oh, 2m. H bar is h over pi.
h over 2 pi.
H over 2 pi.
Okay. And now what's our derivative? Is it a slope or a curvature?
Curvature.
It's a curvature. Okay, so that's T of x. V of x equals 0. So H of x psi n of x equals En psi n of x, or minus h bar squared dx squared psi n of x equals En psi n of x. Now, you guys are good guessers. Tell me a function where the second derivative of the function equals the function times some constants. There's two types of functions that will solve this. E to the, okay,
X
so
power.
this is a differential equation. And there are various formal and sophisticated ways to get solutions, but it is completely legal, moral, and non-fattening to just postulate a solution and see whether or not it works. Okay, so I'm going to show you 4 possibilities. Or any combination of those. So, possible solutions. And I think you guys were kind of guessing pretty close to the mark. Now, why are those important solutions? For sine and cosine, isn't it true that if you take the first derivative, the argument goes out once. If you take the second derivative, it goes out twice. And when you take the second derivative of a cosine, you get a cosine back again. If you take the second derivative of a sine, you get a sine back again. If you take the second derivative of an exponential, you get the exponential back again, plus some stuff.
Are we only going back again because it's a wave? It's just
Oh, no, that's right. This wave equation says the second derivative, there's going to be some constants, but the second derivative of the function has to equal the function times some constants. That's, you don't need a course of differential equations to see this, do you? Because you got a psi n here, second derivative, and a psi n here. You better, when you take the second derivative of psi n, get it back again. So let's take first derivatives of all these things, and then let's take second derivatives of all these things. And then we'll send Phoebe to the pub to drink 3 beers for all of us. Stuck here in America. Okay, so we're going to form the first derivative, okay, ddx of everything. So what's the first derivative of this? There's an A. Derivative of the sine is cosine. Derivative of kx is k. So it's A k cosine kx. Okay. What's the first derivative of the cosine?
It's going to be negative bk sine kx.
Okay, what's the first derivative, Ed, of c e to the ikx?
IK
IKC e to the IKX, exactly right. And while you're hot on it, tell me this one.
Negative KX.
Okay, minus KD e to the minus AKX, right?
Mm-hmm.
Okay. Okay, so there's the function, its first derivative. What's the first, we take another derivative. So to get the second derivative, we take the first derivative of the first derivative. So what's this one?
It's gonna be negative AK squared.
So this is minus AK squared
Sine
sine KX, right? What's the B one?
negative BK squared cosine KX.
And what's this one?
IK.
Now you bring an IK times an IK,
So,
it's K squared, but I times I is what?
oh yeah, negative.
Negative 1. So it's minus
Forgot we're dealing with that.
K squared C e to the I KX. What about this one?
Is it just positive I again? Or is it?
Oh, well, it's minus I times minus I. Minus times minus is a plus, but I times I is a minus. So it's minus K squared D e to the minus I K X.
Alright.
Okay, now, we could take any one of these or any combination of these, and those all have the right form to be a solution because the function is kicked back again with a constant K squared added to it.
Okay.
Okay? So now let's multiply both sides of the equation through by 2m over h bar squared. So we have 2m over h bar squared. And we'll put the minus sign. Oh, yeah, I'll put the minus sign like this. And I'll get d squared dx squared psi n of x equals, and now instead of e and n, I've got minus 2m e of n over h bar squared psi n of x. Oh, this is kind of interesting, isn't it? Okay, because this, we know what the second derivative is, don't we? The second derivative, and let's choose this, the first of our functions. We could choose any of the other ones, so all four of them will work, but I just choose the sign. The second derivative of this function equals minus a k squared sine kx. And then we just go to the function minus 2m e of n over h bar squared. And this is just sine n of x. So this is a sine kx. And now we're going to solve this for the energy. Are you ready? The A sine kx cancels out, doesn't it? And we have a relationship. So we have the relationship minus k squared equals minus 2 times the mass of the particle times its energy divided by h bar squared. So we have a relationship between what this constant k is and what the energy is. In other words, the wave behavior, the oscillatory frequency, the oscillation of the wave function is tied up intimately with the energy. Okay. And this free particle can go from minus infinity to plus infinity, oscillating away, no problemo. Now, this is a high point, isn't it? Let's just finish up in the last couple of minutes. So we have negative signs away. We have k equals the square root of 2 mass En let's see if I did this right, over 8 h bar squared. Or if you wanted the energy in terms of k, we could solve for that too. That's k squared. It's h bar squared k squared divided by 2m. So I have an expression for the oscillation that depends on the energy. And we have an energy that depends on the, if you want to look at it this way, how the wave function is oscillating. And this wave function will oscillate from plus infinity all the way back through to minus infinity with the same values. And this represents a wonderful point of closure for this lecture. Okay? Now, let's give you a little homework before you put that away.
Okay.
Everyone's quitting. That's wonderful. Trust me, I'm ready to quit too. Now, I want you to prove that the cosine works.
Okay.
And that the e to the I works. So I want you to go, in other words, go through this whole thing. Prove to me that b cosine kx and c e to the I kx work. That they solve Schrodinger's equation. So we've solved our first Schrödinger equation. Aren't you impressed?
Yeah. So you could, the wave function of x, or psi of x, just shortly, can you just explain again why you're able to let it be equal to all of these derivatives that end up becoming themselves again?
Oh, okay. Because from the form of the wave function, notice the potential was 0.
Yeah, we're not dealing with that right now.
I've got to choose wave functions whose second derivatives are a constant or a bunch of constants times the function itself. Because I'm going to take the second derivative, multiply by some things on the left-hand side of the equation, and I'm going to have the function itself on the other one. So I'm bound, I have to have that second derivative kick me back the wave function itself, multiplied by some constants. I have no choice. That has to happen.
Okay, I understand.
It's this and this second derivative.
That being said, are these functions used a
And
lot?
these are 4 types of functions.
That are used a lot in these types of
Oh,
equations?
they're all over quantum mechanics.
Okay.
So these 4 functions have the property that their second derivative gives the function back and times some constants. And the times some constants, by the way, works. We find there's a relationship between the oscillation frequency or the oscillation wavelength and the energy of the wave. That's kind of what we expect in quantum mechanics, but we're finding that already. Now, there's one last cool thing. You don't have to write this down. What we're going to find is if we have an infinite wire in infinite directions and the electron can go anywhere, that it can have any energies at once. But what if we shorten this wire to where it's a meter long or 10 microns long?
It only lets you have specific wavelengths.
Those constraints will say only certain energies and wave functions are allowed. And in our next meeting, we will explore that fundamental idea. Done.